Welcome back to the Machine Learning 101 course. In today's lesson, we will learn about the most common type of supervised learning, classification. Quick recap first. We learned about linear regression, which is a type of supervised learning algorithm that is used to predict a continuous numerical value. We trained a linear regression model to predict GPA. In today's lesson, we will cover a completely different type of problem, dealing with categorical labels. We also covered the core concepts of machine learning, underfitting, overfitting, and data cleaning in our past lesson. In this video, we will introduce what is classification and the most common machine learning algorithm used for classification, that is called logistic regression.
The goal of this tutorial is to solve a simple classification problem using logistic regression. If you have followed my previous tutorial, we have learned a lot about linear regression, especially the home prices example. Linear regression can be used to predict other things such as weather and stock prices. And in all these examples, the prediction value is continuous. There are other type of problems such as predicting whether email is spam or not, whether the customer will buy the life insurance product or person is going to vote for which party. All these problems, if you think about it, the prediction value is categorical because the thing that you are trying to predict is one of the available categories. In the first two examples, it is simple yes or no answer. In the third examples, it is one of the available categories. Whereas in case of linear regression, the home prices example, we saw that the predicted value could be any number. It is not one of the defined categories, okay? Hence, this second type of problems is called classification problem. And logistic regression is a technique that is used to solve these classification problems. Now, in the classification examples that we saw, there are two types. So the first example was predicting whether customer will buy insurance or not. Here, the outcome is simple yes or no. This is called binary classification. On the other hand, when you have more than two categories, that example is called multi-class classification. Let's say you are working as a data scientist in a life insurance company, and your boss gives you a task of predicting how likely a potential customer is to buy your insurance product. And what you are seeing here is the available data, and based on the age, the information you have is whether customer bought the insurance or not. Now here you can see some patterns such as young people don't buy the insurance too much. You can see like there are persons with 22, 25, these kind of ages where zero means they didn't buy the insurance. Whereas as the person's age increases, he's more likely to buy the insurance. So you know the relationship, and you want to build a machine learning model that can do a prediction based on the age of a potential customer. So as a data scientist, now this is the job you have been given. Now the first thing you would do when you have this data is you will plot a scatter plot which looks like this. When you have worked on linear regression problems already, the first temptation you have in your mind is you start using linear regression. So when you draw a linear equation line using the linear regression, it will look something like this. Now, how did we come up with this line? For that, you can follow my previous linear regression tutorials. If you think about it, what I can do here is I can predict the value using linear equation line and say that if my predicted value is more than 0.5, so here this is 0.5. If it is more than 0.5, then I will say, okay, customer is likely to buy the insurance. If it is less than that, then he is not going to buy the insurance. So anything on the right hand side is yes, anything on the left hand side is no. Now, of course, we have these outliers, but we don't care about them too much because for 90% of the cases, our linear regression will work okay. Now imagine you have a data point which is far on the right hand side here. So say a customer whose age is more than 80 years, let's say he bought your insurance, okay? Then your scatter plot will look like this and your linear equation might look like this. In this case, what will happen is when I draw a separation between the two sections using 0.5 value, here the problem arises with these data points. Actually, the answer was yes here, but my equation predicted them to be no. So you can see that this is pretty bad when you use linear regression for data class like this. Now, here is the most interesting part. Imagine you can draw a line like this. This is much better fit compared to the previous linear equation that we had, okay? And here, when you draw a separation between using 0.5 value, you can clearly say that this model works much better than the previous one. The question arises, what is this line exactly? And how do you come up with this, right? If you have learned statistics, you might have heard about sigmoid or logit function, and that's what this is. Okay, now the moment you hear this term sigmoid, you might pause this video and start Googling about sigmoid, and it is fine. You can read all the articles about sigmoid or logit function to get your understanding correct on mathematics behind it. But if you don't want to do it, I will give you a basic idea. The sigmoid function's equation is 1 divided by 1 plus e raised to minus z, where e is some mathematical constant. It's called Euler's numbers. The value is this. Now think about this equation for a moment. What we are doing here is we are dividing by 1 by a number which is slightly greater than 1. And when you have this situation, the outcome will be less than 1, correct? So all you are doing with this sigmoid function is coming up with a range which is between 0 to 1. So if you feed set of numbers to the sigmoid functions, all it will do is convert them to 0 to 1 range. And the equation that you will get looks like S shape, right? So if you plot a 2D chart, it will look like S-shaped function that we saw in the previous slide. Essentially, what we are doing with logistic regression is we have a line like this, which is linear equation, and you know the equation for our linear line, which is mx plus b. All you're doing is you are feeding this line into a sigmoid function, and when you do that, you convert this line into this S shape. Okay, so here you can see that my z I replaced with mx plus b. So I applied sigmoid function on top of my linear equation, and that's how I got my S-shaped line.
When we are making a prediction between two options, we call it binary classification. More than two choices is called multi-class classification. We apply a sigmoid function to the linear regression equation to make it non-linear S-shaped curve, which is more suited for binary classification as compared to a line. The output of logistic regression model is a probability of yes. We can convert it into a yes-no decision based on a threshold. For example, if the probability is greater than 0.5, it maps to yes, otherwise it is a no. Last example clarified how to use logistic regression for a binary classification problem. But how will it work if we have more than two classes? For example, deciding whether an input is a triangle, square, or circle. We solve this problem by mapping it to multiple binary classification problems. Instead of training one multi-class classifier, we will train multiple binary classifiers, one for each class. In this case, we will create 3 binary classifiers, one for each shape, and the final prediction will be made based on which binary classifier outputs the highest probability. In case of linear regression models, we use root mean square error to measure the quality. However, in classification problems, the quality metrics are very different.
One way to do this is by creating a confusion matrix for each method. The rows in a confusion matrix correspond to what the machine learning algorithm predicted, and the columns correspond to the known truth. Since there are only 2 categories to choose from, heart disease or does not have heart disease, then the top left corner contains true positives. These are patients that had heart disease that were correctly identified by the algorithm. The true negatives are in the bottom right-hand corner. These are patients that did not have heart disease that were correctly identified by the algorithm. The bottom left-hand corner contains false negatives. False negatives are when a patient has heart disease, but the algorithm said they didn't. Lastly, the top right-hand corner contains false positives. False positives are patients that do not have heart disease, but the algorithm says they do.
quick overview of the most important classifier metrics. Precision measures how often, when the model predicts yes, it is actually yes. Recall measures of all the yes cases, what percentage was the model able to identify correctly. Note that precision and recall are specific to one of the classes. And accuracy measures of all the yes and no predictions, what percentage are correct. Linear regression uses a cost function that is very close to mean squared error. Again, that cost function is not a good fit for logistic regression, and let's understand why. As the final decision is going to be a Boolean decision made based on a threshold, for example 0.5, what really matters is how often are we making the wrong decision. That is, the probability is on the wrong side of the 0.5 threshold. Therefore, if actual label is 1 and the prediction is 0.8 or 0.9, it is reasonably good as both these values will map to 1 after applying the threshold. Hence, cost contribution is small. However, if the prediction is 0.2 or 0.1, the prediction is wrong, and hence the cost contribution should be very high. Same holds true in the reverse direction when the actual label is 0. With that understanding, let's look at the actual cost function used by logistic regression algorithms.
Now that we have knowledge about the sigmoid activation function and the decision boundaries, let's move on to the next part, that is cost function for logistic regression. If you recall, in linear regression, we had the gradient descent. Similarly, in the case of logistic regression, we write a prediction function. So a prediction function in logistic regression basically returns the probability of an observation being positive, that is true or yes. We call this class 1. Now you can see from this graph, as the value gets closer to 1, the confidence level is higher and the cost is lower. Similarly, if our class is y is equals to 0, we see that towards y equals to 0, the cost is minimum. And if we predict the class 0 as 1, we see that the cost is very high. And therefore, this is the graphic. So let's go with this equation. J of theta equals to 1 by m. Summation of I goes from 1 to m. Cost of h of theta x, comma y of I. Now this J of theta is our cost function. Now you must be having a question about why didn't we use the same cost function as in terms of the linear regression. So basically, our prediction here is non-linear because of the sigmoid transformation that we saw. So squaring this prediction, as we do in mean squared error, results in a non-convex function with many local minimums. If our cost function has many local minimums, the gradient descent will not find an optimal global minimum. That is, it will not converge. Hence, instead of mean square error, we use this particular cost function. The name of this is cross entropy. It is also known as logarithmic loss. Cross entropy loss can be divided into two separate functions based on for the class y equals to 1 and for the class y equals to 0. Now the benefits of taking the logarithm reveal themselves when you look at the cost function graphs for y equals to 0 and y equals to 1. These are smooth monotonic functions. That is, they are always increasing or always decreasing, and this in turn makes it easy for us to calculate the gradient and minimize the cost.
This is another representation of the logistic regression cost function that combines the two scenarios y equals 1 and y equals 0 in a single equation. Since this course only covers the basics, we're not going to delve deeper into the cost function. For this lesson's exercise, check out logit_titanic.ipynb. The model we will train here looks at predicting whether someone would survive the sinking of the Titanic or not. The link to the repo can be found in the description below. To learn more, check out these videos about ROC, AUC, bias, and variance. The hands-on exercise can be found in the repo linked in the description. It is about predicting whether someone would survive the sinking of the Titanic or not. To get more practice, check out the problem posed by the problem.md file about classifying an animal as a mammal or not. To see my approach, look at logit_animalbinary.ipynb. In the next lesson, we will go over another type of model, that can be used for classification, decision trees. We will also briefly touch on KNNs, which lie at the boundary between statistics and machine learning.